All right, good afternoon. Today is our last lectures. We're going to finish up 2 examples of AC power. All the topics have been covered. All 7 chapters are completed. The only thing that remains after today is quiz number 10, which is on Monday, last quiz of the quarter. And after that, I'll see you directly on the day of the final exam. I will be here on campus every day. I'll be available for office hours during class times and otherwise in any other time, basically, if students need. And then I'll talk more about that on Monday, the last 10 minutes of Monday after the quiz is completed. Any question? No. I will be available in the office though. I could, yes. It's the same format as the quizzes. Yeah. Same format as the quizzes. No difference, no change. So it should be familiar. The only thing different would be um, the length, 2 hours, and then everybody will not have the same questions. That's the only difference. Okay, so power triangles. I believe we had stopped here. This is power triangle for an inductor. This is power triangle for a capacitor. In an inductor, QL is always pointing straight up, angle of plus 90. Capacitor is always pointing straight down, angle of minus 90. So we use these and we can define a new term known as power factor. Now, you see that the reactive power, the requirements of the reactive power determine the power angle, right? The larger the value of Q, the higher or bigger the angle. If it's purely inductive load, it's pointing straight up, it's 90 degrees, right? It's purely capacitive, minus 90, pointing straight down. We want this angle to be as small as possible. In an ideal system, it would be 0. Hence, we use this, and mathematically, we use the cosine of this power angle, and we coin a new term known as power factor, which is what we did in lab 8. Power factor is cosine of the power angle, cosine theta. And we state it in terms of percentage. Now, let's see. Okay. Ideal value of this angle is 0 degrees. Cosine of 0 is 1. Power factor is expressed as a percentage, 100%. This is the highest possible value. Okay, highest possible value. We also state whether the power factor is leading or lagging. This actually refers to the current in the system. If the current lags the voltage, then we say the power factor is lagging. If the current leads the voltage, then we say the power factor is leading. The only systems where it happens is an inductor and capacitor. Voltage is always ahead of the current in an inductor, which means the current is always lagging in an inductor. On the other hand, the voltage always lags in a capacitor, meaning the current always leads in a capacitor. So, power factor for an inductive load is always lagging. Power factor for a capacitive load is always leading. and vice versa. If we state it's lagging, then we immediately think it's a inductive load or a capacitor. All right. Okay. Also, a few other equations and terms are listed here. This is a right angle triangle, right? Real power or average power on the x-axis, reactive power on the y-axis, and then the hypotenuse joins the two ends of the triangle. And then the fourth quantity is the power angle theta. So you have three sides of the right angle triangle, P, Q, and magnitude of S, and you have the power angle theta. In order to determine any one of these four quantities, you need at least two. Okay. If you have P and Q, you can determine the angle theta. You can also determine the hypotenuse, which is VRMS times IRMS. If you have theta and VRMS, IRMS, you can determine P and you can determine Q. And again, any two of these quantities can be used to determine the other two quantities. Make sense? Right? That is what we'll see in example number 2. So this magnitude of S, VRMS times IRMS, is also defined as the apparent power. Apparent power is VRMS times IRMS. The reason is a different term for this is because apparent power is the effective power that is available in the transmission line. VRMS or RMS values are basically the effective values of the voltages and currents that are flowing in a circuit. So when you have electricians, technicians, or engineers or working on power lines, they need to know the absolute peak value of the voltages and currents. They also need to know what is the effective value of the voltage and current. Okay, so the product of the effective voltage and current, which is VRMS times IRMS, is the apparent power. That is the power that is apparently moving, not apparently, that is the power that is apparent in the system. Okay, hence it is known as apparent power. S is equal to P plus Q. Mathematically, we use the complex number, the imaginary number J. So S is equal to P plus JQ. Rectangular coordinates, when transformed into polar coordinates, give us the magnitude of S. Magnitude of S is the product of V and I. Total complex power can also be determined from this equation. Half VI or half VI asterisk. The asterisk is noting that it is the complex conjugate of the current I. Complex conjugate is the exact opposite pole in the complex plane. The real portion stays as it is. Imaginary portions is on the other side of the axis. A plus JB is equal to A minus JB. These are complex conjugates of each other. The polar form R with the angle of theta is R with the angle of minus theta. Okay. In this equation, half VI asterisk, V and I are both phasor form. Again, S is the total complex power, and so V and I are in phasor form. And then you have the standard power equations, right? Standard power equations, P is equal to V square or R or I square times R. We saw that in chapter 1. It's a fundamental equation. You probably also have seen that in physics, right? P is equal to I square times R or V square or R. Those forms still apply. in AC analysis. Those are fundamental equations. They do not change. Okay. So if you have a resistor, well, and you apply an AC current, or AC current is flowing through the resistor, it is still I squared times R, except it's the effective value or the RMS value. So these equations apply to a resistor, and these equations apply to a inductor and capacitor. For inductor capacitor is the same form, except power associated with a capacitor and inductor is noted as Q, reactive power Q. So Q is I squared times X, or V squared over X. This is true for both inductor as well as capacitor. Okay. These are just some of the equations, the forms that we're going to use. The analysis for this chapter, it's similar to what we learned in chapters 1 and 2, except the math is using complex numbers. And trigonometry, of course. Okay. Everybody ready for examples 1 and 2? All right. Let's bring up example 1. In example 1, we have a circuit comprised of R, L, and C, inductor, resistor, capacitor. We are asked to determine the power for every component. Every component means we need to find power for RLC as well as the source. Okay, we need to find the power for R, L, and C and the source. All right, so before going into all of this, first step, always tell students, of course, what do we need for power? We saw the equations, right? I squared times R, or V squared over R. We need to know the voltage and the current that is flowing through that component. Okay, you have a circuit, whether it's DC or AC is immaterial. You have a circuit, you have these components in there. If you wish to find power for those components, we need to know either the voltage or the current in that component, right? If it's a resistor, we need to know the value of the resistance. If it's an inductor or capacitor, we need to know the reactance, or we can calculate the reactance. But that's all we need. So power equation, V squared over R, or I squared times R. That is what we're trying to get at. Okay. Now, first portion or first part of this analysis is determining those voltages and currents. Now, I have done both. I have determined the voltage and I have determined the current. Students don't need to do that. Students can only, as an engineer, you pick and choose what you want. You can choose to determine only voltage or only current. Okay. Now, first thing to do in an AC analysis circuit is to draw the equivalent impedance diagram. So I converted everything to its impedance. R stays the same. L is converted to ZL. C is converted to ZC. Then we use DC resistive analysis techniques to reduce this to one single REQ. And that is what we are doing. All right, so let's take it step by step. Source supplies the current, goes in this direction. When it gets here, it splits in two. This becomes IR. This becomes IC. IL is the same current as I. All right. IL is the same current as I. And that splits into IR and IC. Now, if you have three resistors in a circuit in such a configuration, what can we do? We can combine R and ZC into one single resistance. We're going to call it ZRC. Now, at this point, if I wanted to take a shortcut, I would apply voltage division. Apply voltage division, find the voltage across ZL, find the voltage across ZRC. Then I have the voltages for the inductor. I have the voltage for the resistor and capacitor. Apply V squared over R, and we are done. Let's take a pause, think over that statement. Any questions? So far, so good. Okay. All right. Since I'm trying to solve and explain all methods, I'm also going to go ahead and do the other way where we determine the current that is flowing through the circuit, not just the voltage. Okay. So if I look at the current that is flowing through the circuit, if I look at the current that's flowing through the circuit, it's flowing through ZL, it's flowing through ZRC. They are in series. And combine them to find one single ZEQ. That is ZL plus ZRC. Apply Ohm's law, and Vs divided by ZEQ will give me the current I. I is V over R, Ohm's law. So let's go ahead and do that. Represent everything by its complex equivalent. Source Vs of t is represented with its phasor Vs, and then complex impedances for inductor and capacitor. Vs is given as 10 sine of 1000 t. We need to write the phasor, so I need it in cosine. Cosine is x minus 90. So 10 cos 1000 t minus 90. Phasor is 10 with the angle of minus 90. ZL, j omega L, or omega L with the angle of plus 90. ZC is 1 over j omega C, or 1 over j omega C with the angle of minus 90. Solve that, and you get these values. J times 1000 times 0.1 Henry gives me J 100, or in polar coordinates, it would be 100 with the angle of 90. ZC is minus J 100. Again, it's complex numbers, but other than that, the fundamentals do not change. You combine resistors in series or in parallel. You can combine impedances in series or parallel the exact same way. No difference. Okay. All right. Once you have that, we can calculate ZRC. ZRC is capacitor and resistor in parallel. So R times ZC divided by R plus ZC gives me a value of 70.71 with an angle of minus 45. Okay. In polar coordinates, it is 70.71 with an angle of minus 45. In rectangular, it is 50 minus J50. The reason I determine the rectangular coordinates is because I need to sum them up in the next step. I want to find ZEQ. ZEQ is the sum of all three together. Get J100, 50 minus J50. The total equivalent impedance, ZEQ, in the circuit is 50 plus J50, or 70.71 with an angle of 45. Right? 70.71 with an angle of 45. And once we have ZEQ, we apply Ohm's law and determine the total current flowing in that circuit. 0.1414 times, not times, sorry, with an angle of minus 135. Minus 135. All right, let's take a pause. Let me know if you have any questions. Okay. Now we can determine total voltage VRC, IR, and IC. Okay. We can find VRC from voltage division, or we can find VRC from I times IRC. It's the same current I right here. The total current coming from the source is flowing through the inductor. It's also flowing through the parallel combination of R and C. So apply Ohm's law, you can find the voltage across the inductor. Apply Ohm's law, you can find voltage across the resistor and the capacitor. The one-step answer earlier was this. If you didn't wish to find the current, we could apply voltage division and find VRC from there. Okay. In either case, it's your choice as to what you would like to use. If a question doesn't state a specific method, students are free to choose whatever they want. But if it says a particular method, then you have to show that method. In this case, it does not matter. So now we have the currents. All we have to do is apply our equations. On the left, it's the voltage. On the right, it's the current. When I apply V squared over R, 0.5 watts. I squared times R, 0.5 watts. No difference. V squared over R gives me minus 0.5 VAR for the capacitor. I squared times R also gives me minus 0.5 VAR. Determine the voltage for the inductor and calculate QL. You should obtain 1 VAR. That'd be good practice. Okay. How did I obtain? Question being asked is, how did I obtain which one? Oh, this one, VRMS and IRMS. Oh, I first found VRC from this division, and then I applied Ohm's law again. So IR and IC. Magnitude of that. So this is the peak value. RMS would be divided by √2. √2. So that's why I have 10 over √2. So question being asked was about this value. So VR I obtained with a magnitude of 10. If magnitude is 10, then the RMS value is 10 divided by √2. Okay, 10 divided by √2. Same thing on this side. Found the current as 0.1. The current is 0.1. Then the RMS value of that current is 0.1 divided by √2. Answer your question, right? So VL, I hadn't determined, but you can determine VL using this equation. It would simply be VS times ZL over ZEQ in order to find the voltage for the inductor. Or you can do I times Z or I times ZL. That would give you the voltage across the inductor. Either ways, apply Ohm's law or voltage division. Okay. Let's take a pause. Let me know if you have any questions. All right. So we found the power associated with the three components. If you apply law of conservation of energy, Total power that is absorbed in the circuit must be equal to the total power that is delivered by the source. So if we add all of these together, we should arrive at the total power being supplied by the source. 0.5 plus J 0.5. Remember, the capacitor and the inductor are opposites of each other. Q for a inductor is plus or positive. Q for a capacitor is negative. So you get 0.5 plus J, 1 minus 0.5. All right, that's the total power. That's the end of the analysis here. But there are two more methods we can use to determine the total complex power directly. And that is given here. Okay. Total power for the source. This subscript S is for the source. Total complex power for the source is the total real power supplied by the source, PS, plus the total reactive power supplied by the source, QS. Well, in order to determine those, we can use the trigonometric identities and equations. Power angle is theta V minus theta I. If we calculated I, we know power angle is 45. From 45, cosine of 45 and sine of 45 times the apparent power, VRMS times IRMS, gives us the real power 0.5, total reactive power 0.5 VAR. The inductor requires 1 VAR. So right here, without the capacitor, the triangle is larger, the power angle is larger. But the capacitor supplies half of the requirement, so it brings it down, and my power triangle only goes up to here, which is what we did in lab 8. Okay, QL pointing up requires 1 VAR, QC pointing down supplies half of that, 0.5 VAR. So power angle is smaller with the capacitor. Is also another way is by using equation half VI asterisk. Sorry, this is the voltage, 10 with an angle of minus 90. I was 0.1414 with an angle of minus 135. Complex conjugate would change the sign of the angle, becomes plus 135. You solve that and you obtain the exact same answer. So there are several ways to approach the problem. If you wish to find only the power for the source, then all we need is the total current being supplied by the source and the total voltage, and we apply any one of these equations at the end of the problem. Okay. Yeah. So question being asked is, why do we use different units for the powers associated to differentiate between all of them? So, and we will see that in the next example. If we say it's watts, so real resistive power. If we say volt ampere reactive, VAR, we immediately know it is referring to an inductor or a capacitor. And then also we need to know the total complex power that is available in the system. So we can't just use the same unit of watts. And so we distinguish between the three. All right, example 2. In example 2, we are not provided with a circuit. We are simply provided with a schematic of a system. That system has a source and it has two loads, A and B. The questions being asked are to draw power triangles for the load, determine the total complex power for the source, and draw the power triangles for the source. So power triangle, power triangle, power triangle. That's what we need to do. We need to draw 3 separate power triangles. So power triangle, again, going back to this slide, right here. Power triangles have 4 quantities, the 3 sides and the power angle. You only need 2 of those quantities in order to determine the other 2. And that is the approach we will take in that example. Okay. Load A and load B, 1 unit of power is given, and then power factor is provided. 0.5 leading, 0.7 lagging. Okay, so let's extract information. Load A, 10,000 volt ampere, 10 kVA. Goes back to that question that was just asked earlier. From the units, we can determine which side of the triangle it is referring to. If this was watts, then it was referring to the real axis, power P. If this was VAR, it was referring to the y-axis, reactive power Q. Because it is volt ampere, it is referring to the hypotenuse of the triangle, and hence it's referring to the apparent power. Excuse me, or the magnitude of S. Okay, again, our triangle has 4 quantities, P, Q, S, and theta. We need only 2 of those to calculate the other 2. In both of these loads, we are given the power angle, 0.5 and 0.7. Cos inverse of 0.5 gives us the power angle for A. Cos inverse of 0.7 gives us the power angle for B. Okay. Now, power factor leading means it is a capacitive load. Capacitive load meaning the power triangle should look like this, pointing down. X-axis is here, y-axis is here. This is pointing down. Lagging indicates it's an inductive load, so power triangle should be pointing up. So for load B, power triangle looks like this, points up. In both cases, power factor is given 0.5 and 0.7. So for load A, if I do cos inverse of 0.5, I get the power angle at 60. In load B, I do cos inverse of 0.7, I get an angle of 45.57. Okay. Let's take a pause. Is everybody with me so far? Okay, to logically approach such problems for AC power, where we are trying to determine the power triangle. Again, power triangle, P, Q, magnitude of S, and the power angle theta. Those are the 4 quantities. We are provided with 2 of those. We can calculate the other 2. That's the approach we are taking. Okay. Again, leading means a capacitive load, power triangle points down. Lagging means inductive load, power triangle points up, plus 90. Okay, so let's see what we have. In load A, I have my theta is 60, and I'm provided with the apparent power, magnitude of S. Magnitude of S is given as 10,000 volt ampere, 10 kVA. Can determine from trigonometric identities. VRMS, IRMS times cosine theta or cos theta is P. Q is VRMS, IRMS times sine theta. That's the first slide we saw for today. Sorry, not there, there. Okay, VRMS times IRMS is magnitude of S. Okay, it's magnitude of S. So all we need to do is perform this calculation. And you have answers for both PA and QA. Let's take a pause. Let me know if you have any questions. Did that make sense so far? Okay, so we're done with load A. Load B is similar, but a little bit different. We need to use other trigonometric identities to determine the other sides of the triangle. So for load B, we are provided with the power factor. From the power factor, we calculated the angle, okay? But we are provided with not with the hypotenuse, we are provided with real power P. So we have theta, and we have one of the sides of the right angle triangle. So this time, instead of using cosine or sine, we need to use tan. Because tan theta is Q over P. So Q can be calculated from that trigonometric identity for tan. Once we obtain Q and we have P, Pythagoras theorem, magnitude of S is square root of P square plus Q square. So we have the fourth quantity. Thus, we have determined all values for both power triangles. Okay. All right. Doesn't matter what kind of problem it is, power triangle, again, for a power triangle, all we are looking at is what two quantities are provided to us out of those four. We look at those and we calculate the other two. Now for the source, simply add them all up. Total power supplied by the source, PA plus PB, so 10,000 watts. Reactive power QA is minus 8660. QB is plus 5101. Total reactive power turns out to be negative. And because total reactive power is negative, it means the power angle is negative, which means it is pointing below zero. It's pointing down, which means it's a capacitive load. Overall, the system is a capacitive load. It's pointing down. So now I have P, I have S. I need to find what the angle is. So Q over P gives me the tan, or tan inverse of Q over P gives me minus 19.59. That's the power angle for the source, minus 19.59. The power factor would be cosine of that power angle, comes out to be 94.21%. And because it is negative, capacitive load, so power factor is leading. Okay, power factor is leading. Total system power triangle, right here. Okay. P is right here, 10,000. This is QS. Calculate magnitude of S. Right there. And then the power angle, minus 19.59. All right, questions? Yes. So let's see. Question being asked is, why is it leading? Oh, right here. capacitive load is larger than the inductive load. So overall, the system is capacitive. So it's negative. Negative means power triangle is pointing down and its capacitive load. That means power factor is leading. Inductive load, power factor lags. Capacitive load, power factor leads. That's noted here in this slide, right here. So power factor, inductive load, it's lagging. Capacitor, it's leading. So if Q is positive, then it's inductive load, it's lagging. If Q is negative, then it's capacitive load, power factor is leading. That's how we know. This is a ton of information and it can get complicated because there are all new equations in here. But to simplify it, just understand the approach. The approach in this problem is that we need to draw power triangles. To draw power triangles, you need four quantities, the three sides, PQS or PQ magnitude of S, and the power angle theta. Okay, that's the approach we are taking for this problem. If we have two of those four quantities, we can calculate the other two. Now, depending on what two quantities we have, we can use sine, cosine, or tan, sine inverse, cos inverse, or tan inverse to determine the other values. Yes. So question being asked is about the units. Units for P, our P is watts, for Q is VAR, and for S is VA. So it's different for three different quantities. So right here on this slide. P is the standard power. So you watts, we already have used that chapters 1, 2, 3 so far. Only in AC, where we have reactive power, where we use volt ampere reactive. VAR stands for volt ampere reactive. Okay. This is volt ampere. This is volt ampere reactive. And by simply inspecting and observing the units, we can automatically discern whether it is a reactive power or complex power, or is it a real power. Okay. Hence the difference. Magnitude of S is also VA. Volt ampere. Right? Other questions? Okay, so homework for this is due on Sunday. If you need an extension, I can extend it to Monday, but there are some multiple choice of fundamental questions about the basics, and then there are some problems. And then let's see what else. Oh, quiz on this topic on Monday. I will be available over the weekend. So if you have any questions regarding this topic, feel free to reach out via email. I can also hop onto Zoom if you need. And then of course I'll be here Monday morning before class too. So again, get started on the homework. This topic can get a little complicated just because of the number of terms that we have. But in order to keep or simplify it, we just approach the problems as we did for DC analysis. Okay, the form and the structure of the equations are not changed. They are still the same. Okay, power is still the same, whether it's for AC or DC. So the terms are different. Okay. All right, so we'll end class here today. I'll pick up here again on Monday. This is, well, basically, this is the end of the material. This is the end of the syllabus. We've covered everything we need to. All topics, all 7 chapters are covered. The only thing that's remaining is quiz 10 on Monday. So after Monday, the last 10 minutes, I'll talk about the final exam. All of the information on the final exam page is current. It's been up there since the beginning of the quarter. The only thing I might update is probably the list of topics. AC analysis and AC power. AC analysis we already tested, filters was tested, and AC power will be tested on Monday's quiz, 40 minutes long. It will not be on the final exam. So do your best to study this weekend, do the homework, understand this, get done with the quiz, and then you're free, but at least free with this topic. And that's one of the reasons, amongst other things, this is one of the reasons we go a little fast in the first few weeks in the month. Now you have time to inhale, exhale a little bit, and then concentrate on the other classes also. Okay. All right. Have a good weekend, and I will see you all on Monday.